Hi, everybody. So we've talked about what makes a world habitable. We've talked about the fact that the temperature needs to stay reasonably constant, just basically so that the liquid water that's on the surface is going to stay in that liquid form. If it gets too hot, it's going to become vapor. If it gets too cold, it's going to freeze. So how is it that a planet is able to regulate its temperature? Wouldn't any just major changes come about and then everything goes haywire and everything becomes extinct on the planet? Well, actually, Earth, and we think most habitable worlds, has kind of a built-in thermostat that's going to keep the temperature the same, and it does that by controlling the amount of greenhouse effect that's present on the planet. So this is called the inorganic carbon cycle, and we say inorganic because the carbon cycle itself also includes photosynthesis and going into living forms, which then die and return that carbon back. We're talking strictly about the non-living carbon, since that's what's going to cause the greenhouse effect. So what we're going to do in this lesson then is I'm going to introduce a little bit of geology so that you can see how the Earth processes in general are regulating this, and then we'll look at the inorganic carbon cycle in particular to see how it maintains that temperature using its kind of built-in thermostat. All right, let's get started. So the key for a planet to maintain its viability is that it has to have active geology. And so by that we mean it's continually recycling the elements, and it's basically the big way you can see that is you can see it as having erupting volcanoes. Let's look at these two bodies here. These are actual bodies in the solar system. You might actually recognize some of them. This is Io, which is a moon of Jupiter. It's actually the most volcanically active body in the solar system. It's continually reshaping its surface from there. And take a look at what you see. What do you notice about the number of craters on these two worlds? Yeah, Io has very few craters, and some of the ones that look like craters are actually the volcanoes themselves. That's because when it erupts, that wipes out any of the cratering record. Now, both of these worlds are getting bombarded by rocks, debris, asteroids, all of that sort of thing. They're getting bombarded almost continuously. However, most of that gets wiped out on Io because of its active volcanoes. Now, here you can see that this is a much more ancient surface. So the moon here has been pelted by all of these different rocks that have been coming in. Most of them happened early in the solar system's history. So this body has probably never been geologically active. For that reason, we think that there is zero chance that a body that looks like this with all these craters is going to be geologically active. And so therefore is not going to have any kind of life going on. So we need active geology to maintain it. Mars had active geology, and then for some reason, its volcanoes actually turned off. At that point, Mars started losing its atmosphere, and the entire planet died. So we're going to look at some of the processes that go on with this. So before we can do that, we need to talk about the structure of a planet. And we'll use Earth as our example, but most planets follow the same structure. So there's an inner core, and this inner core is completely solid and it's metallic. In the case of the Earth, it's made out of nickel and iron from that, but it's completely solid. Surrounding that is a molten outer metallic core. So this is also nickel and iron, but it's still molten, so it's able to flow around. This is actually what's responsible for generating our magnetic field that we'll talk about in a minute. Surrounding that is the mantle. The mantle is what produces essentially the magma that is going to be coming out of the volcanoes and things. It's rock that's under intense pressure, and so it's got an almost plastic-like consistency. So it kind of flows like heated plastic really slowly from that. So it is rock, but it's able to flow for that. Then surrounding that is the crust. This is what you and I are walking around on. Compared to the mantle, it's actually very thin. It's thinnest in the oceans. The oceanic crust is actually extremely thin, and whereas the continental crust can be hundreds of kilometers. We have actually tried to drill down into the mantle. The Russians have gotten closest, but nobody has ever successfully drilled into the mantle. The only kind of cheat exception to that, Iceland is right on the boundary between two tectonic plates. We'll talk about that. But so it's like the plates have separated, and so you've got a lot closer access to the mantle, and so that mantle material has been coming up. Well, they drill wells to drill for hydroelectric power, or for geothermal power, and so they're using that heat differential. And there is one example of where they drilled too deep, actually hit a magma chamber, and the magma actually came out through the well. Technically, they drilled into the mantle, but not really. So surrounding the crust then is the hydrosphere. This is all of Earth's oceans, but it's also all of our lakes, our rivers, all of that. You really want to think about the crust sticking up through the hydrosphere rather than the hydrosphere just kind of sitting on top of it. So Earth would be completely covered in water, except some of our continental plates are much less dense, and so they float up enough, they'll float on the mantle, so that they can stick up out of the water from there. The oceanic plates are more dense, and so they sink down the bottom, and the ocean water flows in on top of them. Surrounding the hydrosphere is, of course, the atmosphere. This is extremely thin, even thinner than the hydrosphere, for the thickest part that you can breathe. And it gets thinner and thinner and thinner, of course, as you go up towards space. And then one that you may not be familiar with surrounding that is the magnetosphere. This is Earth's magnetic field. And as I said, it's being generated by the molten metallic outer core here. We need four things to generate a planetary magnetic field. It has to be molten, so it has to be liquid, it has to be able to flow. It has to be rapidly rotating. It has to be metallic, in which case we mean it conducts electricity. And then the last one, it needs to be convecting. And we've talked about convecting when we talked about stars, but that just means that it's kind of bubbling. So it's not enough for it just to go around in a circle. It has to be kind of bubbling as it goes around. This will generate that magnetic field, and this is what's protecting us from all the dangerous cosmic radiation that's out there. So when this radiation from the sun hits the magnetic field, it travels along the field lines, and it enters the Earth's atmosphere up here in the northern hemisphere, up in the very far northern part of the northern hemisphere, and also down here in the southern part. When that energy comes in, it interacts with the oxygen atoms and the nitrogen atoms in the top part of the atmosphere, and they start to glow. Think about what you know about spectra. If I have a hot, low-density gas, what kind of spectrum am I going to get? I'm going to get emission spectrum. If you don't remember that, you're going to want to go back and check. So an emission spectrum is individual colored lines. So it's kind of like a neon light. This is what's making the aurora borealis, the northern lights from that. It's actually an emission spectrum shimmering up in the upper atmosphere, but it's being heated by the material that's traveled along these magnetic field lines, and then that energy has interacted way up here in the upper atmosphere. Okay? So if any one of those four pieces is missing from the core, you'll lose your magnetic field. So if the core solidifies, if we don't have if it's not geologically active anymore and the core solidifies, well, then at that point, the magnetic field's going to go away. That's probably the most common way to lose a magnetic field. Mars used to have a magnetic field. We can see that in the rocks because there's some rocks that melted and aligned themselves to a planetary magnetic field that is no longer there. So Mars certainly used to be geologically active. It's got the largest volcano in the solar system, Olympus Mons. It's about the size of the state of Arizona and is 3 times taller than Mount Everest. But Olympus Mons no longer erupts. It is completely dead. And Mars is now basically it's a single plate planet. So nothing is moving. You're not getting this continually churning of geology. So Mars is a dead planet. So what heats up that core and the mantle and keeps everything molten comes from a number of different places. Now, we talked about how the core is actually made out of mostly metal, nickel and iron. So when the body was forming, all this was mixed, and so we had the lighter rocks mixed in with all of the nickel and iron. But if you've ever seen like salad oil, the kind of salad oil that comes in a kind of a tube. If you let it sit out, it'll separate itself into its individual components. The densest stuff will sink down to the bottom, then the next dense, the next dense, the next dense, and so on. The same thing happens when this planet is forming, because these things are hitting with the force of hundreds of nuclear bombs. That melts all of the rock. As soon as these things come together and the planet starts forming, it's forming from impacts coming together. So think about it. You're setting off hundreds of nuclear bombs all at once. Everything's going to be melted. Well, when everything's melted, all that heavier stuff is going to sink to the bottom. So almost all of our iron is actually in the center of the Earth where we can't get to it. The iron that we use for making steel and things, cars and tables and things like that, is actually left over from, it's essentially bacteria poop. And we'll get to that. It's from ancient life forms that lived on Earth. Okay? So differentiation is the process that causes everything to separate out. And that's why the most dense things are in the center, the lesser dense is the mantle, and then the least dense is the core, those oceanographic and continental plates that are sitting, the crust, the oceanographic and continental plates that are sitting on the outside. Okay, so just as a review, this is the core, it's the most dense, the mantle is the next most dense, and then the lithosphere, which is the crust, is going to be the outer part and the least dense material. So what can heat things up? Well, the planet is warm, and as long as it stays warm, it's going to stay molten and it's going to have active geology. So, the energy from accretion, from those initial bombardment, that is where it gets most of its initial energy. From after that, the energy, some of the energy actually comes from differentiation. The fact that it falls down to the middle, it's giving up gravitational potential energy. So just like if I were to take this pen and drop it, the pen has potential energy here. As it falls, some of that gets converted into motion, kinetic energy, but some of it actually gets converted into heat. And so the pen is actually a little bit warmer when it hits my hand. I'm not talking about heating from the atmosphere. Even if we did this on the moon, the pen would be a little bit warmer because it's lost some kinetic energy, some potential energy. Same thing is happening to this stuff. As it falls down towards the middle to form the core, it's giving up heat. And so that gravitational energy is going to cause it to give off that heat, and it's going to warm up the planet. Tidal heating, this is what keeps Io so active, because what's happening is Io is orbiting Jupiter, and Jupiter's this big bully. So it's pointed like this, it's stretched towards Jupiter because the stuff on this side of the moon towards Jupiter is getting attracted more strongly than the stuff on the far side. But it keeps the same face. So what happens when it's over here is it gets stretched in the opposite direction. So it's back and forth and back and forth and back and forth. And if you've ever done this, you can take a coat hanger, a metal coat hanger, and bend it back and forth and back and forth and back and forth and back and forth. And it'll get so hot you can leave scars on your kid brother when you touch him with it. I obviously wouldn't know anything about that. But even so the that's tidal energy is also causing the planet to heat up. Solar energy is the obvious way. The sun's shining on the planet, and that's going to heat up the surface of it. And then finally, most of the radioactive material has gone down into the core. Some of it's in the mantle, but things like uranium, plutonium, things like that have half-lives of billions of years. Well, as that decays, that's giving off heat, just like in a nuclear reactor would do that. So that energy from that radioactive decay is also keeping the planet warm. Now, when we look at percentages from this, accretion is only about 10%. I mean, these bombs have hit as these things have started colliding with each other, and so they've given off their heat. And so that initial heat is there, but it's going to get re-radiated eventually. Differentiation is one of the big sources. About 40% of the energy comes from as this stuff is falling together. Tidal energy, well, and especially in the case of the Earth, not much, because the moon flexes us, but not a whole lot. The sun flexes us even less. The moon's gravity is much stronger than the sun's at this distance, only because the sun is so far away. So that's not going to be a huge factor for us. However, with Io, Jupiter is great big, huge gravity, and Io is actually the closest of the Galilean satellites to it. So tiny little Io is getting a whole lot of that stretching going on. Solar energy, realistically, it only heats the very top part of the Earth. And so that's going to heat the atmosphere, but it's not going to heat much of the Earth at all. So when we say about zero, it's just really, really small. Radioactivity is the other big area. And so all of the radioactive decay, I mean, if you think about it, a nuclear reactor produces huge amounts of energy. Now, this is not a reactor. It's not doing fission. It's just decaying. But it's still giving off a lot of energy from that. And because this has half-lives in the billions of years, that source of that heat is going to keep heating the interior of the Earth for a very, very long time. So the two main sources here that we're going to look at, though, are radioactivity and differentiation. Radioactivity is pretty constant. You get what you get. Whatever you were born with, whatever the planet was born with, that's what it's got. So we're really thinking about this other part, this differentiation here. A planet that is bigger will get more energy from differentiation than a planet that's smaller, because once it stops collapsing, well, that's all that you're going to get. So for this reason, big planets are going to cool down a lot slower than small planets. So one of the ways that a planet's going to cool down is through plate tectonics. And if you think back to high school or whatever, we think about plate tectonics, the continental plates are moving back and forth. They're just kind of floating on that mantle. Sometimes they'll dive down under another plate. Sometimes they'll spread apart. Sometimes they'll move past each other like we have in the San Andreas Fault. So all of these things are plate tectonics, and that movement allows heat to be released out from the interior out onto the surface of the planet, and then of course out into space. Anytime a volcano erupts, part of the interior heat of the Earth has been released into space. So volcanism, is going to be another main thing that's causing the Earth to cool from that. The more volcanoes you have erupting, the faster the planet's going to cool. And then, of course, radiation. As the radioactivity releases that heat, it's got to go somewhere. Eventually, it works its way out and it's lost into space. You can't get that back because whatever you were born with, that's what you've got. So, since smaller bodies have less plate tectonics, if any at all, Mars doesn't have any. Once the volcanoes shut off, and you've only got pretty much your radiation, and if you didn't have much of that to start with, you're going to cool off a lot faster than you will a larger body. So let's look at plate tectonics. So this is a really nice animation of what's going on. So convection, remember that bubbling, rises because if the little bubble of magma, that's what's under lava before it's released. If it's heated up, it gets less dense, so it rises up. But the further away it gets from the hot core, then the more it cools. And so it comes around and it starts to fall back down. And then it heats up and it comes back up. And then it cools down and it starts to fall back down. So it's exactly like a lava lamp, like we talked about. So when that happens, then this kind of churning motion actually moves the continental plates. So you can see here that when this rises, these two plates are going to end up separating from each other. And so wherever that lava comes up, it builds a little mountain. And we're going to see this C4 spreading. This is actually going to cause an undersea mountain range. When it comes down over here, it might actually dive under another continental plate and go back down into the core and get melted, and then the whole process starts over again. This is the Pacific plate. This is a drawing of the Pacific plate. And then there are a number of other plates that surround it, the North American plate, for example, and South American plate. So a lot of these are subduction zones, particularly over here in Asia. This is Japan right over here. And what happens is as the plate goes underneath, that plate, all that rock gets hotter and it melts. Where it melts, then it's going to bubble back up to the surface, and that's going to form a volcano. So the Japanese island chain is really just matter from the plate that's the Pacific plate that's going underneath the Asian plate, and it's formed from these volcanoes that are occurring right there. So that when those volcanoes erupt, then that helps bring some of the gases that were trapped in the rocks back out into the atmosphere. Mostly carbon dioxide and water vapor. Those are the two main things that you can get out of a volcano, and that replenishes our atmosphere. Originally, and we'll get into this when we talk about life, but originally Earth had an almost entirely carbon dioxide atmosphere. It was only because there was a certain microbe called blue-green algae that converted that carbon dioxide into oxygen, that gave an oxygen atmosphere now. But basically, most of the volcanoes on the planet are going to occur right here along this edge of this continental plate, and that's why they call it the Ring of Fire. And you'll see there's one big exception right here. Does anybody know what's there? That's the Hawaiian Islands. It turns out there's a weak spot in the crust right there. And so because there's a hot spot underneath it, and so that heats up and it forms a volcano right there. Well, the plate keeps moving, and so that volcano moves with it. And then the next bubble comes up and forms a volcano, and the plate keeps moving. And that's what's forming the Hawaiian Islands right now. And in fact, we can see something called the Emperor Seamounts. They're worn down to where they're underwater now, but coming right along on this path right here, we can actually see the remnants of other volcanoes that passed over this hot spot right here and then got moved on. So there's actually a new island forming off the coast of Hawaii right now. It hasn't yet broken the surface, so it's not officially an island, but it will continue to do so. There's a similar weak spot, a similar hot spot that is right over here in Yellowstone. That's where the big Yellowstone supervolcano that you probably heard about would be. Okay, so we've got all these things going on, and this is what's going to regulate our climate because, as we said, this can replenish our atmosphere. It can take the carbon dioxide that is locked in the rocks and it can bring it back up into the surface. So let's take a look at how this works. So let's say I've got carbon dioxide in the atmosphere. Remember, we're talking about trace amounts. It does not take much carbon dioxide to have a really strong greenhouse effect. So I've got carbon dioxide in the atmosphere. It forms clouds, it mixes with the water vapor clouds, and then that forms carbonic acid. So if you've heard about acid rain, that's what that is. The more carbon you're going to get in the atmosphere, the more this carbonic acid is going to happen. Well, then when it starts to rain, that carbonic acid pulls that carbon with it down onto the surface. So this rain is responsible for removing carbon from our atmosphere. The more rain you have, the more carbon is being removed. So when that rain comes down, that carbonic acid reacts with the rocks. It dissolves the rocks partially, and it forms bicarbonate, which can easily dissolve in water. So that bicarbonate then flows down to the sea, flows down and becomes the oceans. Now, there's a lot of calcium in the oceans. This is coming from basically the shells of all the sea creatures that are there. It's mostly calcium. So when they die, those shells are left behind. Well, all that calcium reacts with the bicarbonate that's dissolved in the water. It combines, and then it forms calcium carbonate. Well, calcium carbonate doesn't dissolve in water as easily, so it sinks down to the bottom. And that pulls that carbon that was originally in the atmosphere, brings it all the way down to the bottom of the ocean. So this is what we're going to see here. It sinks down into droplets on the ocean floor. Well, this oceanic plate is moving. And eventually it dives underneath the continental plate, melts, and forms a volcano. When that magma erupts out of the surface, then it adds that carbon dioxide back into the atmosphere, and so the process can begin again. You see how that works? So I can get carbon, it rains out, that removes the carbon from the atmosphere, which, by the way, is going to lower the temperature of the atmosphere, of course, because it's less greenhouse gas, right? And then it rains down onto the surface. It reacts with those rocks, forms bicarbonate, which dissolves in the river water very easily, flows to the oceans. In the ocean, there's lots of calcium. Combines with the calcium to become calcium carbonate. Calcium carbonate does not dissolve as easily, drops down to the ground, onto the ocean floor, which then gets carried over millions of years underneath this subduction plate in the subduction zone, and then finally gets erupted back out into the atmosphere. All right, so which of these processes puts carbon dioxide into the atmosphere? We're looking on the back side of your page 2 of your class notes. So which of these processes is going to release CO2 in the atmosphere? So that's going to be the volcanism. That's going to be the erupting volcano. So the more that volcano erupts, it replenishes our atmosphere. Earth is losing atmosphere all the time. All planets are. The solar wind strips that off. Some of the atmosphere, the hydrogen and things like that, are light enough that just their own energy, as they heat up, they go off into space. So if we didn't have volcanoes, we would eventually lose our entire atmosphere. Everything would just turn off. Our atmosphere would be gone, and that would be the end of it. We're going to see that that's probably going to be what happened on Mars. All right, so which step pulls the CO2 out of the atmosphere? And the key for that is the rain. The more rain you have, the more carbon dioxide, carbon in the form of carbonic acid, that you can pull out of the atmosphere that way. So this is, the volcanoes put it in, the acid rain basically pulls it out. Now, which step takes the longest amount of time? Volcanoes can erupt in a matter of minutes, right? Rain generally lasts an hour, if that. Might take a few weeks or months for it to get down to the ocean. It takes a few days, if that, for it to sink all the way down to the ocean floor. But this process right here can take millions of years for that, because the tectonic plates are moving at about the same speed that your fingernails grow. So you can see it, you can measure it, you can actually watch it happen. We can see this with the San Andreas Fault, which is another area where we've got two continental plates against each other. You can see it moving. It's not fast enough that you're going to sit there and go, "Oh, look, I see it moving." But you can actually put down a marker and come back a few days later, and you'll actually see that it's moved. But the process still takes millions of years. And so most of the carbon on the Earth is actually locked up underground in these subduction zones, in these oceanic plates that are moving underneath. So as long as that carbon stays locked up, well, then it's not available to replenish here, nor is it available to increase the greenhouse effect that we have. Now, if you artificially drill down, dig up some of that oil, which is carbon-based, or you dig up some of the other kinds of carbon fossil fuels and things like that, now you've taken that carbon that should have been in the ground for millions of years, you've pulled it out and you've replenished it back into the atmosphere very quickly. And that can cause problems that we'll talk about. But this process then allows Earth to be a thermostat. The inorganic carbon cycle acts as a thermostat controlling the Earth's surface. So let's suppose that for some reason I have too much carbon dioxide in the atmosphere. Maybe the volcanoes just erupted, or maybe we dumped a bunch of fossil fuels, burned a bunch of fossil fuels. But for some reason, there's too much carbon dioxide. When that happens, the temperature is going to rise. Why? Because if I've got more carbon dioxide in the atmosphere, I've got a stronger greenhouse effect. Stronger greenhouse effect means the temperature goes up. Well, when the temperature rises, then we get more evaporation of the oceans. And so, as soon as the temperature begins up, the first thing you're going to see is you're going to see more storms. That's your first indication that the atmosphere is heating up. So that water vapor rises up in the atmosphere very rapidly. That causes storms, which then that washes that carbon dioxide back out of the atmosphere. And of course, it's going to continue on its path. Well, when it washes out of the atmosphere, we've got less carbon dioxide in the atmosphere. And so we have a weakened greenhouse effect, and the temperature goes down. And so then the global temperature goes back to where it should be. Same thing can happen on the other side. Let's suppose it rains too much, or for some reason the volcanoes shut down. Well, then I might have too little carbon dioxide if we haven't had a volcanic eruption in a while. So if there's not much carbon dioxide in the water or in the atmosphere, what is going to happen to the temperature on the planet? The temperature is going to go down because I have less carbon dioxide, so I have less greenhouse effect. Well, when the temperature goes down, we get less of this evaporation because it's not as warm. So the oceans don't evaporate. So what happens to the storms? We get a lot fewer storms. So that what little carbon dioxide we have gets replenished, and so we get more and more buildup there because it's not being washed out quite so much. When that happens, then we get a strengthened greenhouse effect, and the temperature goes up. And when the temperature goes up, it goes right back up to normal. And this process has been going on for billions of years. This is what's kept Earth to be basically the same temperature. Yeah, we've had an ice age. Yeah, we've had some hot times, but it's really not varied that much when it comes down to it. And so this keeps our climate stable. So this inorganic carbon cycle is responsible for keeping the Earth's climate completely stable. Now, this can break. So what would happen if plate tectonics stopped? This is what happened on Mars. Mars is a lot smaller than Earth, so it cooled down a lot faster, and so plate tectonics stopped. So I want you to think about it. What's going to happen if plate tectonics stops? So if this piece right here from E to F breaks, well, you're going to be able to follow this on your worksheet, on your practice. But if this breaks, then I'm not going to have my eruption of volcanoes, am I? Well, if I don't have the eruption of volcanoes, I have less CO2. If I have less CO2, I'm going to get less rainfall. The temperature is going to go down, and it's going to get colder and colder and colder. Eventually, it'll get so cold that it'll actually snow, and the atmosphere will snow down onto the surface. So the atmosphere is getting thinner, which means that if it gets thinner, there's even less greenhouse effect, and so the planet gets even colder, which gives you even less greenhouse effect, and the planet gets even colder. And it gets locked into this kind of runaway refrigerator cycle. And so when that happens, then all the atmosphere freezes down onto the surface. The atmosphere gets very thin and very cold. And that's what happened on Mars. So the carbon then ends up in this, on this, what used to be the ocean floor until everything froze. But basically right here, it's step E. All right, let's look at the other. What if something broke raindrop production? So what if for some reason raindrops couldn't fall? One way that this could happen is if the Earth got too warm, or if this planet here got too warm. If it got too warm, then the water would evaporate before it could get all the way to the ground. And so it basically never rains. So if it may rain up in the upper atmosphere, but if it doesn't reach the surface, it doesn't matter. It's still staying in the atmosphere. So here, the B to C is broken. This part still keeps working, all right? So what's going to happen? Think about it. So I'm not going to be washing that carbon dioxide out, but I'm still going to be having my volcanoes erupt. So I'm going to get even more carbon dioxide in the atmosphere, but it's still not raining. because when you get more carbon dioxide in the atmosphere, it's going to get even hotter, which means it's still the water vapor is not allowed to make it all the way to the end. It evaporates before it makes it down to the surface, which more carbon dioxide then comes in. So the planet gets hotter and hotter and hotter and hotter. And this is the runaway greenhouse effect. This is what killed Venus. Venus had basically all of its volcanoes erupt, geologically speaking, at the same time in a very short period of time. So that dumped huge amounts of carbon dioxide into the atmosphere. We don't know why it happened, it just did. So we can find evidence of that because all the surface, all the crater accounts on Venus are all the craters are basically the same, even distributed, which means that the entire surface is basically the same age. So we're getting all these volcanoes are dumping all this carbon dioxide in the atmosphere. That warmed the planet. The planet got so warm that raindrops stopped. Now Venus used to have oceans. It used to be beautiful. It was actually more of a water world than Earth was. But as it got hotter and hotter because of the carbon dioxide, the water vapor eventually started to evaporate. Well, water vapor is even better greenhouse gas. That increased the temperature even more. So the atmosphere is getting thicker and thicker and thicker. There's no more water on the surface of Venus. But then it got up into the atmosphere, and then the sunlight broke apart the hydrogen and oxygen. The hydrogen went off and combined and escaped because it was so light. The oxygen combined with carbon and formed more carbonate rocks here. So that made the atmosphere of Venus be 90 times thicker than it is on Earth. And also the temperature of the atmosphere rose until it was over 700 degrees. So Venus and Earth, Venus, Earth, and Mars all started out basically as habitable worlds. On Mars, because it cooled down a little too fast, and so its active geology stopped, all of its atmosphere froze down to the surface. The planet got very thin atmosphere and it's very cold. Venus went the other way. For some reason, its volcanoes all erupted that dumped too much carbon dioxide into the atmosphere. And so when that happened, raindrop production stopped, and then the planet got much too hot and the atmosphere is much too thick. So all the carbon then ends up here in the atmosphere. All right, so we're going to look at some of the processes that go on between Mars and Earth, and also between Venus and Earth. But some of this you can think about. What if instead of a bunch of volcanoes, what if we suddenly just started digging up all this carbon and burning it as fossil fuels and dumping it into the atmosphere? Now, the planet can withstand some of this. The inorganic carbon cycle will try to compensate for this and wash that carbon out of the atmosphere because it's going to get warmer. You're going to get more storms. So the very first indication that you have a problem, that you're about to head towards the runaway greenhouse effect, is you're going to get superstorms. You're going to get really large volcanoes. You're going to get all these really large hurricanes. You're going to get lots of superstorms moving through. We're already seeing that, of course. Now we're seeing way more Cat 4s and Cat 5s within superstorms that are moving through, even on the coastal regions and things like that. The first thing that's going to happen then is the ice caps are going to start to melt because the temperature is heating up. So as that happens, that water from the ice caps are going to raise the sea levels. Well, of course, we're already seeing that as well. But eventually, once all that ice is gone, that ice is absorbing most of the heat that's being released. It takes a lot of heat to melt ice. Once that's gone, all of that is going to go directly into the ocean. All that heat that's being produced in the atmosphere is going to go directly into the oceans. The oceans are going to start to evaporate. Well, that's going to add more greenhouse gases. The raindrop production is going to turn off, and basically Earth is going to become a lot closer to being like Venus from that. We'll all be dead long before then because the planet will just be basically unlivable to humans. So, on that pleasant note, what I want you to do is pull out your practice then, and we're giving you the specific example of Venus and Mars. We want you to go through the thermostat process here, go through the inorganic carbon cycle. So what happens to the planet temperature? What happens to the size of the polar caps? Things like that. Work your way through that. If you're having trouble finding that, and especially even if you just want to check your work, come on into live help. Let's go over it because it's real important. This is probably one of the most important things that we're doing. I mean, finding aliens is cool, but realistically, this is what's going to affect your life more than anything else over the next several years. All right? Okay, so now you kind of understand how the Earth is trying to maintain its temperature and how it's managed to maintain its temperature for this long. And now you can start to see how if we get too much carbon dioxide in the atmosphere, we can get that temperature up to the point where we can break raindrop production, and then we're toast. So the Earth will do its very best to try to get that temperature down. It's going to rain, it's going to storm, we're going to get lots and lots of raindrop production as the temperature goes up. And we're already seeing that. Realistically, we are already past the point of no return. Some people will debate, oh, well, global warming is not really happening. Well, okay, only an idiot right now would say that global warming is not happening. Everybody can see the effects of global warming. And they say, well, maybe it's happening, but humans didn't cause it. Who cares? That's my response to this. If humans caused it, okay, let's fix it. If humans didn't cause it, okay, let's fix it. I still don't want to die and have the planet wiped out. Whatever's causing it, we understand the process. Now, you could make an argument that we were simply in one of those regions where it's gotten warmer, but the inorganic carbon cycle is going to fix it like it has in the past. That would happen if we had a linear temperature increase. Instead, what we have is an exponential temperature increase. So the rate at which the temperature is increasing is increasing. That's how we know we're on the runaway greenhouse effect. And frankly, it's too late at this point. Even if we were to eliminate all of our carbon production, then basically there would still be too much carbon dioxide in the atmosphere. Right now, we're just trying to reduce our carbon so that we can come up with some sort of technological solution to save the planet from that. Because at this point, guys, we're toast. So it's going to be your generation that's going to have to figure out a way to get us out of this mess. Good luck. We'll see you next time.